Hi guys. Some of you have told me that you needed some more help with the molecular geometry. So I'm going to do a short little video and see if I can help you with that. So the first thing we're going to do is we're going to draw some Lewis dot structures. So I'm going to take us from the very beginning, walk us through, and I'll pick up the pace as I go through this a little bit more. So for some of you, this might be a little too basic. For some of you, it's exactly where you need to start. So we're going to start with water. And so when we do our Lewis dot structures, please remember that you have your electron math. And so what your electron math is it says with hydrogen has one valence electron. But since I have two hydrogens, that's going to give me a total of 2 valence electrons. Oxygen has 6 valence electrons. And so with these 2 valence electrons and the 6 valence electron in my Lewis dot structure, I need to represent 8 valence electrons. Hydrogen is never central, so that means our oxygen is going to be central in this case. I know that oxygen has 6, so I'm just going to go ahead 1, 2, 3, 4, 5, 6. I'm just going to put them around the way. Then I have hydrogen, so I'm going to put hydrogen where there's the single one because I know a bond's going to form. I know that hydrogen has 1, oxygen has 1, and so they're going to share in order to form this bond. So I might as well just set it where I think it's going to go to begin with. You can always move things around, but however you choose to do it. So a bond does form. Now keep in mind, I can't just keep those 2 valence electrons there because a line represents 2 electrons. By having those electrons on the end of it, it looks like I have 4 valence electrons there, and I don't want that to be the case. So I'm going to erase them and draw a line. Mrs. Dorman, why do we have to erase them? Because it's convention. It's what it's expected to do. I'm not nitpicky on much. This I'm nitpicky on. And so once we do that, since each line represents 2 valence electrons, the one it got from hydrogen and the one it got from oxygen, this line represents 2 valence electrons. So I have 2 there, plus 2, which is 4, 6, 8. Oxygen now meets the octet rule. It has 8. It's complete. It's stable. Hydrogen is one of our exceptions. Hydrogen only requires 2 valence electrons to be stable because it only contains the 1s orbital. And so here, hydrogen has 2, hydrogen has 2. So it is complete. It is stable. So now we get into the idea of how do we know what shape it is? Well, there's 2 ways to do this. One is with a table, and that's the kind of cheater method, and that's fine. You have that available to you. However, when we're looking at this, we should kind of be able to tell what shape it already has. There's only one thing you need to know, and what you need to know is this is called, let me do a different color here. This is called a lone pair. Whenever we have electrons by themselves, we're not going to spread them out on different sides. We're going to pair them up. We're going to match them up. And so this is referred to as a lone pair. When they become bonded, I'm sure you can guess what this one's called. This is called a bonded pair. Well, one thing you need to know about these is that because the bonding pair, they are bonding, there's some attraction there. The lone pair are completely repulsive forces. There's no attraction between them. They're not bonding. And so because of that, they have more repulsive force than the bonded pairs. The bonded electron from oxygen is attracted to hydrogen's positively charged nucleus. Hydrogen's electron is attracted to oxygen's positively charged nucleus. But these electrons are straight just repelling each other. Yes, they're attracted to oxygen's nucleus, but as far as they're concerned, they're completely repulsive. So that's very important because once you understand that, a lot of times the shape is kind of intuitive and you kind of know how to figure out what the shape is. So since I said the bonding pairs are strong, or the lone pairs are stronger, more repulsive than the bonding pairs, you can imagine that these are going to push this down a little bit. And so that's exactly what it does. And when it does that, what we get is where we have water. And water is a bent molecule. If you look at your sheet, you will see that it's not only bent, but it's bent at an angle of 104.5 degrees. Now, another way to do this, the way to use your chart, because I said the chart's the cheater method, and that's perfectly fine. when you use your chart, one thing that I like to tell students to do while you're kind of figuring things out is remember when we were drawing our electron dot structure way back when, and I wanted to make sure you only put 2 electrons maximum on one side. So I told you imagine it's like there's a box surrounding it, or imaginary box, and only 2 electrons can fit on each side of the box. Do you guys kind of remember that? If not, that's okay. The only reason I mention is because we're going to bring that box back. So once again, we're going to bring our imaginary box, and I'm following the rules. I've got 2 valence electrons on each side. So I've got 1, 2. In this case, my valence electrons are my bonding pair. And then I've got those 1, 2. I just want to make them darker so we can see them. So with this box, the important thing now is that each side of the box represents one region. So this is one region, this is one region, this is one region, and this is one region. Kind of like a northeast, southwest. The difference is that unlike northeast, where you can have northeast kind of between them, there's just the sides. So there's just a maximum of 4 regions that this central molecule can have, and each region is one side of the box. So with that one side of the box, when I look at this, I can see that I have 2 lone pair regions. I have 2 bonded regions, which gives me a total of 4 regions. If you look at the chart that I gave you, the table, your molecular geometry table, you will see that where it says the central atom has 4 regions, 2 lone pair, 2 bonded, you will see that it tells you that that molecule is bent with an angle of 104.5. That is how you use the table. So now that we know that, let's kind of go on and do another example. So in this case, let's look at another favorite, which is ammonium, or ammonia. So I've got NH3. Once again, we're going to do our electron math. So my nitrogen has 5 valence electrons. It's in group 5. My hydrogen has 1 valence electron, but there's 3 of them. So it's going to have 3 valence electrons for a total of 8 valence electrons. Once again, hydrogen is never central. So my nitrogen will be central. And I'm going to have 1, 2, 3, 4, 5 that go around nitrogen. I'm going to just distribute my hydrogens on either side because I know that's where they're going to bond. My hydrogens have 1, and that's exactly what happens. They're going to bond. So those will bond. Don't forget to erase those extra electrons. That's a common mistake, is that you'll leave them there. And then you count them and get all confused as to why your electron count isn't correct. So now when I look at this, hydrogen is complete because it has 2, has that one s orbital. So we've got 2, 4, 6, 7, 8 around nitrogen. So nitrogen is also complete. Now once again, before we go to the table, let's look at this. If you remember what I said up above, my lone pair has a much stronger repulsive force than my bonded pair. So that means this lone pair is going to push these bonds down a little bit. And that's exactly what it does. When the NH3 molecule forms, what's going to happen is this nitrogen is going to seem like it's raised up. It's pushing these down. And so it's going to seem like it's raised a little bit. And if you ever notice in pictures, not always, but a lot of times, people will draw that bond back here as if it's shorter. It's not any shorter. The bond lengths are still the same. The reason why it looks shorter is because keep in mind this is really a 3-dimensional molecule, 3D molecule in 2D space. So this hydrogen is really going into the paper. And so by the angle that you're looking at it, this is actually as if it's going away from you. I'm not much of an artist. You guys know that, but it's really going away from you into the paper. And so then we can tell this, the nitrogen ends up standing up. The 3 hydrogens are at the bottom. And so if we look at our table, so we're going to do our imaginary box again. I want to get rid of these arrows first. When we do our imaginary box, it's going to look something like that. Once again, I have 3 bonding regions. I have 1 lone pair region, for a total of 4 regions. And I notice that on my box, all 4 sides of my box are being interacted with. And so with those 4 regions, I look at my table, 4 regions, 1 lone pair, 3 bonding, and it tells me that it is a trigonal pyramidal. Now, I know some of you, when you have to memorize these names, are sitting there thinking, I'm never going to remember these things. It's actually not that bad. Once again, if you remember that these bonds are pushing these down, so then you're going to get it where it looks like N is at the top, and that's exactly it. If you were to draw kind of imaginary lines here, this would look like a pyramid. Keep in mind that this is going back into the paper. So when things form, this would be a pyramid. And a pyramid is a triangle. It has 3 sides on each face. So it's a trigonal pyramidal. The name really does actually make sense for once. I know scientists don't always do that. Let's look at 1 or 2 more. So next, what if we have something like C2H2? Carbon has 4 valence electrons. There are 2 carbon, so there's going to be 8 valence electrons total. Hydrogen has 1 valence electron. There's 2 of them, so there will be 2 valence electrons total, for a total of 10 valence electrons that we should show in our Lewis structure. Carbon always goes central. Well, but there's 2 carbons, Mrs. Dorman. So we're going to put them side by side. And we know our hydrogens go on the other side. You'll notice that this time I'm not drawing my dots. I told you we'd kind of start taking some quicker steps. So once you get used to doing the dots, if you still need to draw the dots and then connect the bonds, go for it. You do that. But if you've gotten to the point where you're familiar enough and comfortable enough, you can just draw your bonds. So here, my hydrogen has 2, it's complete. My hydrogen has 2, it's complete. My carbons don't. My carbons only have 1, 2. So that means that each of them still have another electron. I'm going to put them like this because, as I said up above, those electrons don't exist single, they exist in pairs. And so I'm just going to go ahead and put them in those pairs in case if this is how it stays. So when I look at my carbon, I have, remember that this counts for 2 when it's carbon's turn with the electrons. So I have 2, 4, 6. I have the same thing on my other carbon, 2, 4, 6. So this carbon is not complete. It's not stable. So what I can do is both of my carbons have extra electrons. When you have all of your electrons that were over here, when you have all of them accounted for, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't add any more unless this was a negatively charged polyatomic ion. I can't add any more. And so I'm stuck with these 10, but I can rearrange the 10. And so I can share this carbon's electron with this carbon. And when I do that, that's going to make a second bond between the 2. And so that it helps me down the road of completing this. Now this carbon has 2, 4, 6, 7. This carbon has 2, 4, 6, 7. So it's still not complete, but they both still have an electron that can contribute to a bond. So that's exactly what's going to happen. And now I have 2, 4, 6, 8. And then this one has 2, 4, 6, 8. My carbons check, and they're good. So now what I need to look at is, well, what shape is this going to be? Well, you should be able to tell that by looking at it. There are no lone pairs. And we know that because of repulsive forces, things are going to be as far away from one another as possible. Well, as you can imagine, with this triple bond, these carbons are kind of restricted in their movement. So really, kind of side by side is the only place they can go. So then the hydrogens are going to be on opposite sides because that's as far as they can go. So right now, how we have it written looks like what we might expect it to be. So we're going to pick our central carbon. Which one's central? Well, if you'll notice, it's a mirror image. This carbon is attached to 1 carbon and 1 hydrogen. This carbon is attached to 1 carbon and 1 hydrogen. So it doesn't matter which one I pick. I'm going to pick this guy. So there's my imaginary box. And in this case, I noticed that there are only 2 regions being interacted with on this box. Yes, this is a triple bond, but remember what we said. Each side of the box is a region. Even though this is 3 bonds, those 3 bonds are only reacting with one region. So I have 2 bonded regions, 0 lone pair regions, for a total of 2 regions. When you look on your chart, you will see that that is in fact linear. Hopefully some of this is making some sense. Okay, so for our last one real quick, I'm going to come back up to my water, and I know I don't have a lot of space on this, so this might get a little interesting. I'm going to erase our electron math over here, and I'm not going to do the electron math for this next one to try to save some space here. So now what I want to look at is, this time I'm going to look at, just pick something simple. So I'm going to do CH2, okay? We said that our carbon had 4, and I know that I'm going to have 2 hydrogen. So here's a hydrogen, because that's just where I'm going to put them. And I'm going to have a lone pair, because carbon, 1, 2, 3, 4. Okay? So with this, once again, if you remember what I said, these lone pair are going to have more of a repulsive force than these bonded pair. So that's going to cause these to be pushed down. However, since there's only one lone pair that's pushing in both directions, this bond angle won't be as severe as what it was on our water. And so what I mean by that is, if you notice over here on our water, I had 2 lone pairs. So not only are those lone pairs repelling that bonded region, they're also repelling one another. So they're trying to push as far away as they can. They're repulsing as much away as possible. Since there is only one pair here, it's not going to have as much of a repulsive force as if you have 2 that are pushing. And so because of that, this is still bent, but we have a different bent. Remember that the water's bent was 104.5 degrees. Well, in this case, our bent is going to be less than 120 degrees. And that's why it's possible to have 2 bent molecules that have different angles. It depends on how many lone pair and how many bonded pairs. And so that really comes down to the crux of the matter. What determines molecular shape? Molecular geometry. And what it comes down to as far as molecular geometry is concerned is the number of lone pairs and the number of bonded pairs and how they interact. Lone pairs have more repulsive force than bonded pairs. And so that is what is causing the shape of these molecules. Hopefully you found this helpful. I will do another video next on bond polarity and molecular polarity. To watch as I stop this now. Bye!